Okay, we're back and we're rolling. Okay, so we got the change in x 2.2. We can show that as this horizontal segment, and then the corresponding change in y as the vertical segment. And how much is the change in y? 5.28. And then to get that constant rate, you took 5.28, the change in y, divided by 2.2, the change in x. Okay, so this number, 2.4, what does it mean? So, yes, it's the constant rate of change of y with respect to x. But what's that? What does it mean? Yes, sir.
For every 1 unit we go, for every 1 unit of change in x, we're going to have 2.4 units of change in y.
He said for every time we go 1, we increase x by 1, or the change in x is 1, the change in y will increase by 2.4. What do you think? Good interpretation. Is there another way to interpret that, 2.4? That's an excellent interpretation, but can we say it another way? Yeah. You got the right idea, but our words are important. So you want to adjust that? Yeah, so another way to say that is, or another way to interpret that value is that changes in y will always be 2.4 times changes in x. So now, not just a change of x of 1. Every time x changes by 1, y goes up 2.4. But if x changed by 2, how much would y go up? 4.8. And if x goes up 10, how much would it go up? If x goes up 10, how much does y go up? 24. Why? Because the change in y is always 2.4 times the change in x. Okay? So these, in terms of, we're now talking about linearity. And we're using constant rate of change to motivate how we think about linearity. These are the two main ideas, or the perspectives of constant rate of change that we'll be using when we're dealing with the mathematics of linearity, or setting up the equation of a line, or working with a line. Okay? All right, good. So then I think it asks you, the next thing it asks you about is something about x equals 7.2. Is that right?
Yeah.
Okay, so now we want to find out what the new value of y, so if x started at, so it doesn't matter, we can start here or there, but let's start here. If we started here, and we want to know if x changed to 7.2, what would the new value of y be? And this process that we're about to do is the process that we want to use to build the equation of the line. So we're gonna do this process for a specific value of x, and then we're going to repeat the same process again for any value of x, and by doing it that way, then we generate the whole line, every point on the line. Okay? So now I've got a starting value of 5.1 and of x, and we want x to change to 7.2. So what's the first thing we want to know? Yes, Farah? Change of what? Good. Okay, so we can represent it this way. And how do we calculate that change in x? How'd you get that? Good. Is that the change in x? And how much is it? 2 point? Is that right? Okay. And our goal is now the resulting value of y. So what would come next in that process if we want the resulting value of y? Where's Ali? Yeah. So we got the change in x. What would come next? So basically, somewhere up here is the new point. What's the x coordinate of that point? 7.2. The y the new value of y is what we're after, okay? That's what we're after, the new value of y. So we've got the change in x, 2.1. So what would we do next? Yes, sir?
You multiply it by 2.4.
And what would that give you?
That would give you 10.32.
No. Why are you doing that? What does it represent?
Because it goes back to the equation without the y 2.4 times delta x.
Okay, so the next thing we want is the change in y.
Yeah.
So the change in y is always, what? 2.4 times the change. And in this case, what's the change in x? 2.1. So what is our change in y when x changes by 2.1? I heard 5.32? 04? How's that look? Good? How do we represent it on the graph? Can you all see it? Draw it with a finger. As x changes from 5.1 to 7.2, or changes by 2.1, y will change by 5.04, right? Because changes in y are always 2.4 times changes in x. Constant rate of change. Is it right? Are all my numbers right? Oh, I should have started 2.9?
Okay, cool.
Oh, I started at a different point. Do you want to just keep on this one, or do you want to start over? Just keep on this. It's the same thing. You can start from 2.9. You're going to get the same value. So if you already finished that from 2.9, we'll see if you get the same thing. All right, we'll keep going. Sorry. We should have started here and gone out to 7.2. Okay, are we good now? Okay. How are we going to find the new value of y now? So we got this new value of y. What does it equal? How can we get that new value of y? 5.04. Yeah, so it should make sense. We started at a value of y, we changed y. So if you add that change to the old y, you get the new y. So what was our change? What was our change in y? 5.04. What was the old y? 10.44. Add them together, what do you get? 15 point? If you started from this point, 2.9, 5.16, and did the same process, you should get the same answer. Okay? You should get the same thing. That's our new value of y. Okay, so again, the idea here is that we're forming this linear function. Okay, by drawing that black line, what did I just draw? I drew points, right? What I'm representing is all the points, the corresponding pairs of x and y. I drew all those points. Okay, that's what, when you see a graph from here the rest of your life, it's points. That's what it is. The reason we do it that way, why? Because that took me a second, but truly drawing what it was, all the points would take all semester, all college career, all your life to draw all those points. So we do it in a second, but we know what it means, right? We know what it means, the points. So now we want to go through that same process again so we can represent every single point, say x, y, okay? We want to go through this again. We want to represent every point on that line, x, y. So let's do it. Let's start from, we started from 5.1, now we'll start from this point. And so what we're after is to represent the line, which I'm now drawing as a series of points. So we can pick any one of these. So I want to pick this one right here, okay? And that's going to be our final point, x, but it represents any point on the line. So we call it xy. So here's our initial point, 2.9, 5.16. And we're going to go to the point, and by going to just a generic xy representing any point on the line, and by going through the process of finding that value of y, so our goal is, what does that equal? We get the equation of the line. We get the equation of the line. Okay? So what's the first? Do we do the same process? What's the first step? Where's Daniel Flores? Daniel. First step, tell me. We're going to go through the same process again, starting at our lower point there and ending at xy. What's the first thing we want to do in this process? Which one first? X. And we can represent that with that right there. There's our delta x. How do we calculate delta x? What will it be? Daniel, keep going. Final point. But our final point is any x, right? starting point 2.9. So how would we show that change in x from 2.9 to x? No, where's Caitlin? She wants x, so final value of the quantity, minus initial, right? Because x can be anything now. X can be anything. So Caitlin, keep going. What's the next step in the process? Where's Caitlin? Yeah, can you keep going? What would be the next? We're trying to get this in the end. So we got our delta x. What would come next? Remember? G, can you help her? I know you are. I'm trying to break that. I'm trying to break it. Yeah. Times delta x. All right, and that's represented here. This is our delta y. But we know what delta x is now, right? What is it? X minus, it's right here, x minus 2.9. Remember, changes in y for this line, changes in y are always 2.4 times the change in x. And our change in x is x minus 2.9. One more thing, and what are we after? We're after this value of y. We're ready to write what it equals. Who's next? Where's Moises? Can you do it? What is the value of y?
Just put 2.4 x and distribute it.
No, we want y now. So remember, we have the starting value of y, 5.16, and we want to know what's this final value of y. Remember what that principle was? Yes. Yep. So we started at the old y, and to get the new y, we're going to do what? Add the change in y. Should make sense. What was our old y? 5.16. What's the change in y? 2.4 times x minus 2.9. There's the change in y. There we got it. Now we've just written every single point on that line. X and y, right? Given an x, it'll crank out what the y is. So the nice thing about this is we know what everything means now. See, we know what this means. What is this right there? What is that? That's the change in x from the point 2.9. So you start at 2.9, you go to any other new value, that'll be your change in x. What is this right here? Given that change in x, we know exactly what the change in y is using constant rate of change. And then, what's the 5.16? Starting value of y. Old y. And so now our new value of y is the old y plus the change. So the nice thing about this form is we can look at that and we can see, oh, it's based on the starting point of 2.95.16. Our constant rate of change is 2.4. And we know that we get our whatever our new value of y is by adding the old y plus the change in y. Okay, so I'll just humor you for a second. Now, if we were to evaluate that, what would we get? We get 2.4 times x, and then we'd have 5.16 plus the product of those two, right? Which turns out to be negative 1.8. So minus 1.8. And you all know what that minus 1.8 means. What is that minus 1.8? Okay, if x were 0, you get this value of y, negative 1.8. So coming down here, it's like this. So there's another, this is your y mx plus b form. So what is the slope of the line? What does it mean? What does it mean, the slope? 2.4. No, it doesn't mean you're on the run. Yeah, that's the constant rate of change. That's what the slope is. It's how much y increases for a unit change in x, or how much the y changes, the multiple, the constant multiple on change of x to get the change in y. All right, and then this is our value of the starting point. So I want to define, let's start here. Start at 5.1, and pretend you didn't know that was. We don't know the y-intercept. If we didn't know it, how could we use the process still one more time, starting at this point, to find the y-intercept? See if you can do it. Take a minute and see if you can use the process again, starting at the high point, 5.1, 10.44. Do the process again to confirm or to check in a different way that the y-intercept is negative 1.8. Go, see if you can do it. Does that make sense? So this is your starting point now. And our finishing point is this y-intercept. So go through the process to figure out what that is. Pretending you didn't know. Pretend you don't know it's negative 1.8. Oh, sorry. Not there. You're starting here. You're starting here. Starting at 5.1, 10.44. Our final position is the y-intercept, and that's what we're trying to find. Where's Jonathan Clark? Did you get the first step of this? What would you do first? All right, so delta x, he wants delta x first, and he wants x minus 5.1. So where does that, how should I draw delta x from here? What should I do? Just delta x. Where would I stop? Where would I stop? So this particular x minus 5.1, where should it stop? I want to go to this point because I'm finding. Okay, and so now can you be more specific then? What should this be? What is my final value of x then? 0. So the change in x is? Negative 5.1, right? And there it is right there. So now it's going to the left because it's a negative change in x. That's okay. You can handle that. Final value of x is 0 because we want the y-intercept. Starting value of x is 5.1, so that's a negative value of delta x. So it goes back to look like this. Okay, where is Jonathan Leeson? Yeah, what's next?
You already know the change of y with the change of x, so you multiply the change of x by the change of y to get the change of y.
Multiply the change in x by what? By the constant rate. That's right. And that equals to what? I mean, what are we finding? Oh, change in y. So the change in x is our negative 5.1 to get back to that y-axis. Corresponding change in y will be? Meaning we'll go down negative 12.24 from that point. So it's right there. It is negative, that's our change in y. And it's negative 12.24. Okay, one more step. Where is Patrick? Cowger. Is Patrick here? Andrew Guerrero. What's the last thing? Which is 10.44. Started at a y value of 10.44, and then? Which is? And we're thinking and saying that's going to be? There it is, right? It worked. New value of y, negative 1.8, and that's what we got when we did the equation of the line, too. Okay, so why do we do this? Why? Because everything in the process has meaning, and it keeps our focus on how the quantities are changing together. If there's a change in x, you have an associated change in y. And that associated change in y is determined by the constant rate of change. So that's what calculus is about. Changes in one quantity and associated changes of the other. All right, and so we're going to form our linear equations based on this idea of how the quantities change together. And we're starting with a very particular type of what we call covariation, which is constant rate of change or linear constant rate of change. Yes, sir?
So in order to find y, what the y intercept we have to change x equals 0.
Right, so on the y-intercept is on the y-axis. So what's the value of x on the y-axis? 0. Yeah, so that's the first thing we do. If we want the y-intercept, is your final value of x will be 0. Yep. Other questions? Okay, so I'm just going to make up let's see, we'll start again here so I have some space. Can I erase everything up there? Not too late now. Okay, here we go. So here is our line. What am I drawing right now? All the points, right? All the points. We know this is negative 1.8. So let x equal the time elapsed since the basketball game started in seconds. So x is a time quantity. X is a time quantity. And y is the distance of the moving camera to the right of the left basket in meters. So have you seen these awesome cameras that hang on wires? And they zoom around at concerts and at sporting events and give you awesome views of the action, like kind of overhead or coming around the players or whatever. So imagine you're looking at the basketball court and there's the left-hand baskets over here, right? So as time goes by, this thing is moving to the right, and the y value is the distance in meters from the right to the right of the left-hand basket on the court. Okay, so my first question is, does this make sense down here? Can't have a negative distance. What do you think? So can we conceive it? Can we make a real world conception of it? Yeah, it would mean what? What would negative 1.8 mean? It starts to the left. It starts 1.8 meters to the left, and the game starts, and what happens? Yeah, it starts moving. As time goes by, this thing starts moving, the camera, and what does that mean right there? Where's the camera? At the left basket, right? And time keeps going, and it keeps moving at a constant rate to the right. Okay, so what's the speed of the camera? Someone said 2.4. 2.4 what? Meters per second. Okay. Is that distance over time? Yes or no? Is that distance over time? Okay. Isn't our distance quantity y? And our time quantity x? So I want you to find y over x for this one, and find y over x for this one. Go. Find y over x and y over x for each of those. This should say b-ball game. Sorry, game. Anyone get the first one? 2 point or 1 point, was it? Nice and loud. 1.78, cool. All right, and the second one, nice and loud. 0 point. As soon as you get it, shout it out. Nice and loud. Oh, sorry, not 0 point. 2 point what? 2 point, thank you. 2.05. What do you think? Is the speed distance over time? You're telling me it's distance over time. You're telling me it's the y coordinate over the x coordinate, which is 1 point, which is... Okay, so be careful. So we've got two different quantities. We've got the distance to the right, and we have the change in distance. And we have time, and we have the change in time. So speed is really what? The change in distance over the change in time, or delta. That's our delta y or delta x. Remember, that's how we got the 2.4. So just be careful saying that speed is distance over time, because here's an example where I'm dividing distance by time, and I'm not getting the speed of the camera. You see? It's not the speed of the camera. The change in distance over the change in time. That's our constant rate in this case. That's our speed. Make sense? Any questions? Okay, speaking of speed. 12 million views.
There is the full lineup. Every single one of the men in this lineup has run 100 meters in less than 10 seconds. Bolt, Gay, Powell, 4, 5 and 6. They're away. Quick start by Daniel Bailey. Usain Bolt though getting into his running. Here he comes. Usain Bolt challenged by Tyson Gay. Usain Bolt 2 clear meters. Tyson Gay in second place. And in third place is Suffolk. 9.58! Smashing the world record. Unbelievable! He's done it again! A year later, rewriting the world record.
Let's see.
There is the full lineup. Quite as quick as some of the others in the race. But Steve, once he gets into his running, we've never seen the like. No, you cannot understand. A year later.
All right, that's fine. Whatever. Okay, I wanted to get him in a nice flying pose. Okay. Anyway, so how do we calculate his speed? I heard distance over time. What do you think? Change in distance over change in time. Okay, so I'm way off here. What was this distance? What race this was? The 100 meters, right? This is the test to see who the fastest man in the world is, right? 100 meters. What was it? Okay, and he shattered the world record. His change in time was 9.58 seconds. So find his speed. Find his speed. Someone got, what is it? Meters per. Is this right? Rounded to the hundredth of a meter? 4.4? Okay, got it. 10.44. All right. So, question is 10.44. What does that number mean? 10.44 meters per second. So let's have one person. What does that number mean? Somebody new. Angelica.
Every second he covered 10.44 meters.
Every second he covered 10.44 meters. What do you think? This is Justin, right? Okay. It'd be a constant rate of change. Okay, so she said every second he covered 10.44 meters, and Justin said it's a constant rate of change. Somebody new. Who else wants to chime in? Yes, sir.
That's an average rate of change.
Average rate of change.
He wasn't going 10.44.
Yeah, so when he ran the race, every second that went by, did he go 10.44 meters? He didn't? I thought you told me this was his speed. What happened at the beginning of the race? Slower or faster than this? Slower. What about the end of the race? So you're telling me he went slower and then he went faster, but then when we calculate his speed, we get this number. Someone's saying average. Is this like adding all your test scores together and dividing by the number of test scores? No, it's not. What does this mean? Average speed or average rate of change?
If you calculate the amount of time it took him to run the 100 meters, if you separate that out evenly into the time that he ran it, then you would get 10.44 as the.
So what are you talking about when you say that? What are you talking about?
If you were to keep the same speed,
Okay.
then that would be good.
If he would have kept the same speed, yeah.
If you plot it on the graph, you run the curve, but you put a line through it, that's it.
Okay, well that's a representation. We want to really understand what this number means. What this number means. Anyone else? Give it a shot.
If you started going that fast at the very beginning,
Yep.
and ended that fast, that's how long it would take.
What about in between?
Same speed.
So they're all talking about this being what kind of speed? This is a constant speed, right? Isn't it? But he didn't run at a constant speed, right? So what constant speed is that? If it represents his race, what constant speed is it? The constant speed that would do what? So if that's representing his race, it's representing his race, right? But he didn't run at a constant speed. So what constant speed is that if it represents his race? Yeah. Yeah, that's how we got the number. That's how we got the number. And so we get this constant speed. So what constant speed is that? Is it his max speed? Someone said.
That's not his rate, but that's not his change.
Okay, I recreated the race here. I recreated his race with my software here. So this is his time. This is time elapsed here. And that should show pretty accurately how he ran the race. Okay? His number on his leg is the point at where he's at. Okay? So if he starts at the line, 2, 1, go. He runs slower at first, and then he gets his top speed, and he kind of holds his top speed. He actually slows down a little bit at the very end. Okay, so he's slower and then faster, and then he slows down just a little bit at the end. Okay? So what is this 10 point? Was it 10.44? The average of the high and the low speeds? No. So you all know it's the average. So now we're really thinking about what is this thing the average speed? What is this? We just get one number that characterizes his whole race. So we should know what that number means. Yeah? Okay, so that's the magic word right there. This is a constant speed, right? So we'll go back to that question. What constant speed is it? What constant speed is 10.44 if it represents his race? Okay, yeah, what's that? Who's that? It's Emma. My baby Emma. What does the 10.44 mean? Here we go. Ready? 3, 2, 1, go. What is average speed? What is average speed? Right here.
If you were to take acceleration, then the acceleration making way, you would just say, if you were going at a constant rate, or if you were to go 10.44 meters in this yard, you would go 100 meters in 9 point whatever seconds. That's how many meters you'd be going per second.
Okay, it's got the right idea. So this number, this average speed is.
Does the baby represent the constant speed of 10.44 meters per second?
Does the baby represent the constant speed of 10.44 meters per second? Yes. So if it's a constant speed, then it's also his what? His average speed. That's what you told me. We got this from his race, and you told me that's his average speed. But that's the constant speed of the baby. Here she goes, ready to go. She's a fast baby. And she can run at a perfectly constant speed. So what is average speed? Is, first of all, it's what kind of speed? Constant speed. Average speed. So lots of you are thinking this, but we're going to put some good words to it. Average speed is the constant speed. I'm going to do this better here. Okay, so average speed. Okay, can you just hold on 1 second? Just so it's not noisy and distracting. Average speed is the constant speed to do what? To cover what? Same distance in the same amount of time. That's what average speed is. It's like another runner that goes at a constant speed and covers the same distance in the same time, just like what the baby does.
So they both have the same
No, the point is that the baby's constant speed represents the average speed of Usain. That's the point. The baby is like the constant speed that represents the average speed of Usain, because the baby covers the same distance in the same time. Yes. So the average of his average speed on a race is a constant speed. It's the constant speed to cover the same distance in the same time. So her constant speed represents his average speed, because she's running at a constant speed. See?
Mr. Ashford,
Sir.
I wanted to introduce myself.
Yeah.
I was emailing you back and forth. That was when I was gone.
What's your name?
Scott.
Or your son?
Yeah.
Or your dad? Isn't it?
Yeah. So I was gonna meet you in your next office period to kind of tell you what I went over there and what I can kind of do.
Okay. Can you come tomorrow? You come tomorrow?
Yeah.
12:30.
Yeah, and I've seen. I watched the videos 1 through 3. I didn't get to 4 yet because I have good Wi-Fi.
Oh, good. Were the videos clear enough?
Yeah, no, they were great.
Okay.
Just the terminology I got down pretty well, like the quantity and stuff. So I tried that for the recitation today.
Okay.
I got 6 and 7 down, and then I'll finish up the videos today and try.
So I need to put up all the web work for you. Not web work, right?
It's up there.
Oh,
like
it's up there.
I did, but I can't like do it. So I did the August 28th one, and the one after that. I tried that, but it wouldn't like save. So I can do it. All the problems wouldn't.
Because the answers are already submitted.
Yeah.
Yeah. If I would have remembered, I would have just let you. I would have actually assigned it to you.
I didn't look at the answers. I did like kind of trial and error, like actually tried them.
Yeah, that's great. That's great.
So,
Okay. But we'll
yeah.
talk tomorrow.
Sounds good.
Yeah.
When's your office hours? Thursday?
12:30 to 2:15.
12:30 to 2:15. All right.
Are you in the 9 or this class? You're the new class.
Yeah, yeah.
Okay, so you weren't here when I called roll, so just when did you come in?
I came in like 10 minutes
10
after
minutes,
because
okay.
I walked around in the
Okay.
building.
Perfect. All right.
Alright,
See you tomorrow.
Is it okay if I have a station today, but can I turn it in the written homework on Friday?
That's up to him.